Hello, my name is Jacob Adams.
Hello, my name is Serta Kinner.
Hello, my name is Bradford Davis.
Hello, my name is Jassim Al-Falakawi.
I'm Zachary Helblick, and we are 3D Metal Printer Team 1. We sought to make an affordable and dynamic 3D printing platform that could support the production of metal products. We achieved affordability by integrating a metal inert gas welder into a 3D printing platform similar to the RepRap series of 3D printers. In order to automate our welder, a relay was used to control the welder's extrusion through G-code given by the logic board. We also tried to create a welding safe enclosure to allow testing in a safe environment to allow all participants and allow one to view the welding process to make sure that the printer is working properly.
The backbone of this project is the MIG welder. MIG stands for metal inert gas. The MIG welder operates much like a conventional FDM printer in the sense that both heat the extrusion of build material. Three main things happen with the MIG welder. 1, extrusion, 2, shielding gas, 3, current. This allows material to be built up onto the platform to build our 3D object. Geometric code, or G-code, is what almost all automated machines run on in industrial applications. Such applications consist of robotic arms, CNC machining, plasma cutting, etc. Our 3D metal printer runs on G-code, which makes it very versatile for industrial applications. Unlike what is conventionally thought of 3D printers, most operations are actually 2.5D, which consist of a bunch of 2D planes built up on the Z-axis.
Our 3D printer is the skeleton of our project. A 3D printer allows for the movement in the X, Y, and Z axis. A 3D printer was donated to us, and the components of the 3D printer that were used were the shell of the 3D printer, the stepper motors and drivers, the limiter switches, and the wiring, along with the power supply. Here we can see the 3D printed MIG clamp that allows for the attachment of the custom head of to the 3D printer. Here we can see the 3D printed, here we can see the electrical diagram as long with the SKR 1.4 turbo that is connected to the relay. The relay is connected to a fan, which allows for extrusion when the fan is being powered. This is done by G-code to turn on and off the fan when the printer is printing.
For our base, we tried using a copper plate, but our welding filament did not stick to the copper plate at all. So there was no way to stack the welds on top of each other due to filament movement. The second experiment was with an aluminum plate, but the penetration were inefficient. The steel plate was the subject of our most recent experiment. With the steel plate, we were successful, and the welding the top of the steel was efficient. It was difficult to attach the clamp on the 3D printer, so we added a hole for a bolt and nut to thread through, giving the welder a more secure ground.
The prime advantage of the casing is that it works great at trapping heat and controlling the thermal environment around the printer. At the same time, it closes the material particles which otherwise could easily be inhaled and might lead to serious health complications. Next slide. So for the casing, we have designed a casing box to protect the welder and the surrounding from the fire spatters. In order to keep the casing safer, we decided to tint the glass so we can keep it safer and protect the eyes from the bright light. However, we tint the glass, it's still not safe, so we decided to use a welding curtain and cover all the sides to reach the highest safety standard. For the fabrication, we used aluminum to build the casing box so it can be light and easier to carry around. We used 4 pieces of plexiglass which would enclose it from all 4 sides, and an aluminum sheet to cover the bottom, and the top will be open so we can use it as our working area. The thickness of the plexiglass that we are using on all of the sides is 0.5 millimeters, so it would be thick enough to endure the heat. Next slide. And this is our final look of the casing box. Next slide.
Here's a few of the important standards that we focused on in this project, mostly dealing with safety because of the health concerns of this project dealing with a welder. We can move on to the next slide. This is a current configuration of our project. On the left, you're going to see the tank and the welder there. Following that line, you're going to see that's the welding head or the MIG head. That's connected to the 3D printer. On the base, you're going to see one of our testing plates on there, and it's enclosed within the case. The case is tinted dark, so you can barely see through it. And we're moving on to the next slide. On the left is our first set of tests before using the relay to control the welder. The first 6 rows are all 1 layer high and at all different feed rates. This test was to calibrate our welder to get the correct feed rate matching our movement speed. Row 7 is 2 layers high at the same feed rate as row 8, while row 8 is 6 layers high. This at the same feed rate of row 4. This was produced in 3 minutes and is 100 millimeters long. On the right is the one used with the relay to control the welder. We manually created G-code to write HI in the plate. This test was successful. This showed that it is possible to low-cost integrate a welder into a 3D printing platform and automated its extrusion with G-code. Next slide. Here's just a real sped up 3 times video of our 100 millimeter wall being built, 6 layers high. So it's going to do passes back and forth. As you can see, the bead is very clear and nicely put and is very smooth. We would like to express our gratitude and thanks to everything that was donated to us, specifically the 3D printer by the Bionic Glove, as well as every professor that helped us, specifically Professor Zabtahi, Mr. Perry, Mr. Fred, Mr. Nan, and any professor who attended this presentation. Thank you so much and have a great day.